Hello and welcome to this calculus video. Today we will be talking about implicit differentiation.
Math 112.
We now know how to differentiate a large number of functions. Recall, though, that we define the derivative to be able to find the tangent line to a curve. Most people learn the word tangent when referring to circles, so let's try and compute the tangent line to a circle. The circle centered at the origin of radius 1 is defined by the equation x squared plus y squared equals 1. All our rules for derivative work for functions y equals f of x. However, the circle is not a function of x because it doesn't pass the vertical line test. If we attempt to solve for y, then we get two functions because of the plus minus square root, and this corresponds to the upper and lower semicircle. We could differentiate each of these expressions using the chain rule, and this would give us the slope of the tangent line. However, we had to do a bunch of work in solving for y, and our solution wasn't even unique. The circle is an example of a curve that is defined implicitly by an equation. An explicit equation gives one variable as a function of another variable. An implicit equation does not give one variable as a function of the other. Here are three examples of implicitly defined curves. None of these curves can be easily expressed as a collection of functions because the algebra is hard. So how could we find the tangent line to such curves? The trick is to not attempt to solve for y at all. Instead, we imagine that y is some unknown function of x and attempt to differentiate the expression as is. Whenever we differentiate an expression involving a y, we use the chain rule and differentiate the expression of y as normal and remember to multiply by y prime. This is called implicit differentiation. In our circle example, we differentiate both sides of the equation with respect to x. On the right-hand side, we get 0 because we are differentiating a constant, but on the left-hand side, we get 2x plus 2y prime. Note that the extra y prime comes from our application of the chain rule to the unknown function y. We can solve this equation for y prime. We find that y prime equals negative x over y, which actually agrees with the derivative computed the long way. Let's take a look at a second example. The folium of Descartes is defined by the equation x cubed plus y cubed equals 6xy and looks like this. As you can see, there is a part where vertical lines intersect the curve in three different places. So if we were to solve for y, we would get at least three different functions. Just for fun, one of the solutions look like this monster. So, to find the tangent line to the curve, we won't solve for y. Instead, we will differentiate implicitly. On the left-hand side, we get 3x squared plus 3y squared y prime. And on the right, we get 6y plus 6xy prime. We can solve this whole expression for y prime, which gives the slope of a point on the curve in terms of its x and y coordinate. Beware, our expression for y prime is a function of both x and y, and makes sense for values of x and y that are not on the original curve. Now let's see a more theoretical application. Recall that the inverse function to a function y equals f of x is the function such that f of f inverse of x equals x, and f inverse of f of x equals x, i.e. the inverse function undoes the function. For instance, the inverse function to x plus 2 is x minus 2. The inverse function to x cubed is the cube root, and the inverse to e to the x is ln. Let's say we want to compute the derivative of the inverse function, y is f inverse of x. We can apply f to both sides of this equation and get f of y equals x. Differentiating this implicitly gives y prime f prime of y equals 1, and so y prime equals 1 over f prime of y. Using the equation y equals f inverse of x, I find that y prime is 1 over f prime of f inverse of x. But y prime is exactly the derivative of f inverse of x, so we have found a formula for the derivative of the inverse function as long as we know the derivative of the original function. That's all for now, folks. Today we learned the process of implicit differentiation, which we can use to find tangent lines to curves defined by an implicit equation. We also applied this to allow us to differentiate a function that is the inverse of a different function.
Math 112.